Today we are going to talk about sequences, which is in section 9.4 in your book if you care to look that up. A sequence is an ordered progression of numbers. You have heard this referred to before as a pattern. An ordered progression of numbers, or a pattern, is what we call a sequence. We have two different types of sequences here. Finite sequence stops. Alright, so it's a set number of numbers in your pattern and then it stops. We also have something called an infinite sequence, which continues on, and that assigns a unique number a sub n to each natural number n. So natural numbers are our counting numbers. We could plug in any number that we want to into a formula, and that's what we will talk about as an infinite sequence. You can keep going and going and going with those. Alright, so here is a pattern of numbers. If you look at this table, n is the term number, so our first term in our sequence is 2, our second term in our sequence is 5, the third is 10, 17, 26, 37, and 50. Alright, so there is our sequence. Right now, this is a finite sequence. We have 7 terms and that is it. Alright, so if you look at these numbers, hopefully you can see what the pattern is. From 2 to 5, we have added 3. From 5 to 10, we have added 5. From 10 to 17, we have added 7. Then we add 9, 11, and 13. So if I ask you for the next term in the sequence, or the next 5 terms in the sequence, now that you recognize the pattern, you should be able to do that. So if we wanted an 8th term in the sequence, we would add 15 to the 50, so the 8th term in our sequence would be 65. Alright, so that's what we're talking about with a sequence, or a pattern of numbers. Alright, so this does say provide the next 5 terms of the following sequence. We have already found the next one, which was 65. Alright, and we got that by adding 15. Next we would add 17, so 65 plus 17 is 82. Alright, then next we would add 19, which will take us to 101. Then we would add 21, which will take us to 122. And then lastly, we would add 23, which would take us to 145. Alright, and we could keep going on with that if we wanted to. That one just asks for the next 5 terms, so we have written those. Now, this question says, can you create a function that would generate this sequence? In other words, can you create a function so that for the first term I could get it by just plugging in the 1 into the function. For the second term I could just plug in a 2. So we're going to let you take a look at that and see if you can create a function so that when you plug in 1 or 2 or 3 or 4 or so on into that function, that you would be able to generate those numbers. So take a look at that, see what you can come up with, and we will talk about that in class tomorrow. Alright, so this next slide says find the first 6 terms and the 100th term of the sequence a sub k, is how we read that, in which a sub k equals k squared minus 1. So in the last example, we ask you to see if you can come up with a formula to generate those numbers. This one, the formula is given. A sub k is k squared minus 1. Alright, so to get the first term, or the a sub 1, that means the first term of our sequence a sub k, all we have to do is plug in a 1. Alright, so I'm going to write this out so you can see the steps. K squared minus 1, but in place of the k we're going to put a 1. So 1 squared is 1, minus 1 is 0. Alright, so the very first term of our sequence, or a sub 1, would be 0. Alright, same thing for a sub 2. All we have to do is plug that term number, okay, or this value here, the k value, we would plug it into our formula. 2 squared is 4, minus 1 would be 3. So the next term would be 3. Alright, and if we continue on with that, 3 squared is 9, minus 1 would be 8. 4 squared minus 1 would be 15. 5 squared minus 1 would be 24. 6 squared minus 1 would be 35. Alright, so that is pretty simple to just plug those numbers in there, square the number, and subtract 1 to get those terms in my sequence. Alright, And same thing for a sub 100. This is no more difficult other than the number is larger. We're plugging in a 100, so we're going to do 100 squared, which 2 zeros and 2 zeros, that's going to be 4 zeros. So 10,000 minus 1, which is 9,999. So the 100th term, I know we're skipping a few in between the 6th term and the 100th term, all right, but that 100th term would be 9,999, and we get that the same way we got all the other ones. We just plug that number in. All right, so there are two different ways that we can write sequences. There's what we call an explicit formula, which is a definite formula. We just saw one of those where it told us that a sub k was the k squared minus 1. That was an explicit formula. We also have what's called a recursive formula, and that relates each term to the previous term. Okay, those of you that have been through Math 1, Math 2, Math 3 know this as a next now rule, that the next term is based on this current term or the now term. So that is not a formula that you can plug into. To get the next term, you would actually have to know the term before it. All right, so two very different ways of writing these sequences. All right, so this says find the first 6 terms and the 100th term for the sequence defined recursively by the conditions. All right, so this looks very similar, finding the first 6 terms and the 100th term, to what we did a minute ago, but instead of this one being given as a formula where you just plug in the term number, this is written recursively. So look at how this is written. B sub n equals B sub n minus 1 plus 2 for all n's greater than 1. All right, so this says to get the term that you're looking for, B sub n, you're going to take the term before it. That's what B sub n minus 1, the one before it, one back from this one, and we're going to add 2. All right, so this recursive formula tells us that to get the next number, all we have to do is take the one before it and add 2. So the pattern is going to be that we're adding 2. So if our very first number, our very first term is 3, okay, then we automatically know what that is. And with this recursive formula, I really should back up and box a little more than I have boxed. These recursive formulas always have to tell you a term. You can't know, if you're adding 2 to every one to get the next term, you have to know either where to start or you have to know some term along the way. So this is very important that it tells you that the very first term is 3. All right, so we just copy that down. Now the second term is this current term, the B sub n minus 1 plus 2. So we're going to add 2 and we're going to get 5. The next term we're going to add 2 again and we're going to get 7, and so on. So the fourth term would be 9. The fifth term would be 11. The sixth term would be 13. All right, so that is what we call recursive formula. The next one is based on the one before it. Now, B sub 100, to get the 100th term, we're really going to have to think about this because we can't just plug in a 100. We're adding 2 every time. We know that's the pattern. But we're going to have to think about how many times do we need to add 2. All right, so I'm at the 6th term now, and that's 13. I could just sit here and add 2 and add 2 and add 2 all the way up to 100, which might take a while. Even in your calculator, if you add 2 and then just keep enter, 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 that's going to take a while. Or we could think about how many 2's do we need to add. All right, we already have the first term, which is 3. To get from the first term to the 100th term, we don't need to add 100 2's. We only need to add one less than that. We only need to add 99 2's. All right, because we already have the first one. We need 99 past that. So we're going to take our starting number, which was our 3, and we are going to add 2 99 times. Okay, we're going to add 2 99 times. All right, so if we do that math, 99 times 2 is 198. And when we add the 3 to that, we're going to have 201. So our 100th term is 201. All right, so we really have to be smart right there in figuring out a term number that far down the road. Think about how many of those numbers we need to add. We had to add 2 99 times. This example we just looked at is what we call an arithmetic sequence. We have two different types of sequences, arithmetic and geometric, and we're going to take a look at both of those. Arithmetic sequences have a common difference. In other words, you are adding or subtracting a number each time. Okay, so the pattern on these arithmetic sequences is that we are adding or subtracting a number every time, and that number is called the common difference. That D is called the common difference. So if you look at this, we're starting with a number, we're going to add the common difference, then we're going to add it again, so now we've added it twice, all the way up to we're only going to add it n minus 1 times. And we saw that on that last example for the 100th term. We did not need to add that common difference 100 times. We only needed to add it 99 times, which is exactly where this n minus 1 comes in, 1 less than the term number. Recursively, the formula is a sub n equals a sub n minus 1 plus d. So this says to get the term that we're looking for, we take the one before it, a sub n minus 1, and we add that common difference. Explicitly, or in other words, a formula that we could just plug in the term number that we're looking for if we wanted to, is a sub n equals a plus n minus 1 times d. And again, that example that we did where we only added the 2 99 times comes from this formula here. Okay, so that is an explicit formula where if I wanted the 77th term, I could just plug in a 77 and plug in my starting number and very quickly figure that out. Alright, so this says find the common difference, the 10th term, a recursive rule, and an explicit rule for the following sequence. Alright, so let's first look at this and see if we can figure out the pattern. -6, -2, 2, 6, and 10. Alright, so hopefully you can see that what we're adding each time is 4. Each of these is going up by 4. So 4 is our common difference, which we call D. Okay, so that is, common difference is 4. It asked me to write a recursive rule and an explicit rule, and it also asked me to find the 10th term. I think finding the 10th term is going to be easier after we have written these rules. So let's write the recursive rule first, and this is the one that bases the next term on the term before it. So our recursive rule is going to say a sub n equals a sub n minus 1 plus 4. What we're doing to get the next term is we are taking the term before it and we're adding 4. Now what's important to also write with our recursive rule is where we started. Okay, it doesn't matter if we know we're adding 4 each time if we don't know what value we started with. So we always have to put our very first term, which in this case is -6. That is our very first term, and we would go up from there. So there's our recursive rule. Our explicit rule, if you look back at the formula that was given to you, that rule says a sub n equals a plus n minus 1d. Alright, our a is our starting number, which in this case is -6, our very first term, plus n minus 1 times d, or our common difference, which in this case is 4. Alright, so we could simplify this just a little bit if we wanted. If we distributed the 4 and rearranged it to, be in the order that we normally see it, 4 times n is 4n. The 4 times the -1 is going to be -4, put together with the -6 is going to be -10. So now I have an explicit formula that I could plug in any number. And you might want to check one or two of those out. If I plug in a 1 for the first term, that should give me -6. If I plug in a 2, 4 times 2 is 8 minus 10, that should give me the -2. So I would always plug in a couple and make sure that it does what it's supposed to do. Alright, and then for the last question that says find the 10th term, now that we have an explicit formula, all we have to do is plug in a 10. So if we're looking for the 10th term, we would do 4 times 10 minus 10, which is 30. So the 10th term would be 30. Alright, so we have found the common difference, the 10th term, recursive rule, and an explicit rule for this example. Alright, we will come back to these other examples in class. For your homework